Alright guys, hello and welcome to lesson 2.10. We're going to do integrals that involve exponential functions with the base of e. Alright, so as you guys remember, the derivative of e is e. Pretty cool. So, not surprisingly, the integral of e is e. We just don't want to forget to put plus c. Okay, and so that's what we're looking at today. Now, all of the problems we're going to be looking at today involve u substitution, okay? And usually, not always, but usually, the u will be whatever the power on the e is, okay? So for number one, then, for instance, I'm going to let u be equal to 5x minus 3. Take that derivative. Dx by itself, and now we're going to go ahead and rewrite the expression here. It's now going to be the integral of e to the u du over 5, and then we're going to take that 5 out in the denominator there. We have that. So when you're doing integrals that involve e, most of the time the u is going to be the power. Okay, so we did all of our u substitution there. Now we just get to integrate this. So the integral of e is e. We don't want to forget our plus c there. And we also don't want to forget that we need to put the u back now. So it was 5x minus 3. There you go. So that's the basic idea there. Usually the u is what's in the exponent, all right? So let's go ahead and do, let you try one like that really quick. Why don't you guys try number 1 on this student practice. Pause the video, and when you unpause it, you'll see the solution. And there's your answer, so I'll let you guys study that, see if you have anything you want to ponder for a minute. But just so you guys know, anytime your power on the e is of this form, right, your answer is always just going to be what you had with a c, and whatever the slope of that mx plus b was, you're just going to put that in the front, but as a reciprocal. Okay. Now that's not going to work on every problem. Like for example, it's not going to work on 2, 3, or 4. But it does work anytime you have an integral that looks something like this. So I mean, if you want to take a minute and just think of that as an extra little formula to write down, you can, because it will work. Okay? But let's not forget where it really comes from. It comes from doing u substitution. So let's go ahead and take a look at number let's see. I guess we could do number 2. Let's do number 2. Now, number 2 is a definite integral. We have numbers here, which means we're finding area under the curve. Now, this exponent right here, this is not y equals mx plus b, right? That's not an mx plus b, so that little shortcut I just showed you is not going to apply to this particular problem. Okay, so we have to just do it the regular way. But here we go. We have u is equal to x squared plus x. The derivative of u with respect to x is going to be 2x plus 1. And we get the dx by itself. Let's do our u substitution. So we have 2x plus 1. We have e to the u. And then we're going to replace dx with du over 2x plus 1. And once again, nicely, those things end up canceling. Now, we're not done, though, because when we have definite integrals, we also have to transform our limits, right? So, if I were to plug 1 in for x, what would the u come out to be? Well, 1 squared is 1, plus 1 is 2. And if I plug in 0, 0 plus 0 gives me 0, so that's 0. So now I have the following. And since this is a definite integral, we're going to integrate it, and we're going to put brackets around it. And then we do our little fundamental theorem of calculus where we write it twice. One where you plug in the 2, one where you plug in the 0. And anything to the 0 power always equals 1. So here would be our final answer, e squared minus 1. And in case you guys forgot, e is just a number. It's like 2.71. So even though it looks like a variable, it's not a variable. It's actually a number. But there's our answer. That would be the area under the curve. So throw one of those at you guys now, a definite integral involving the e. Let's see. I think you guys can handle it. I believe in you. I want you guys to try number 4, a little bit of a trig. Don't let it fool you. It looks really ugly. Just remember, this is your u. Start off by doing your u substitution, and when you're done, it should come out looking a little bit prettier. So go ahead and pause the video, give it a try, see what you get. Alright, so first of all, we let u equal cosine, find the derivative, which is negative sine, get the dx by itself, and then we do our u substitution. So we have sine x, e to the u, and then du over negative sine x. The sine x's go away, and we have a little negative here, which I'm going to put in the front in the next step there. But we also need to fix our limits. My limits were pi and 0. So if you plug pi into cosine, you get negative 1. So now pi becomes negative 1. And then we're also going to plug in 0. Cosine of 0 is positive 1. So the 0 becomes positive 1. So now my limits are from 1 to negative 1, which is interesting. They're backwards. Usually the bigger one's on top, smaller one's on the bottom. But in this case, that's not how it's coming out. So we're going to leave it just as it is. So we have the negative in the front, because when we took the derivative of cosine, we got negative sine, and so that kind of came out there. And then we've also changed our limits. So at this point, we're ready to integrate. The integral of e to the u is e to the u. We have the negative in the front, and then we have our two limits of negative 1 and 1. We go ahead and do the fundamental theorem of calculus. So we have negative e to the negative 1 minus negative e to the positive 1. So I stopped here because that's where you would stop if you had an FRQ, but multiple choice, we want to keep going here. So these double negatives in the middle here become positive. E to the 1 is just e. And then for this first one here, it's e to the negative 1, which is 1 over e, right? Now, we can combine these together by getting a common denominator. So I could put this over 1. I can multiply the top and the bottom by e. And that way I will end up with a common denominator of e. And so on the top I have a negative 1 and a positive e, so you could write that as negative 1 plus e squared, or I like to put the positive 1 in the front. And that would be the simplest answer there, e squared minus 1 over, over e. And there you guys go. Okay, so that would be, this would be the multiple choice answer here. This would be the FRQ answer there. Okay? All right. Remember, you don't want to simplify it if you don't have to on a free response question, because you can get it wrong and then be sad. We don't want to be sad. All right. So, as I mentioned to you guys a little bit earlier, usually the u is the power, right? And that's what the past two problems have been. But for number 3, that's not the case. Now, how are you going to know when it's not the case? Well, first of all, look at my power. It's just an x anyway. We would never let u equal x, because if you did that, that's not going to do anything helpful for you, because all it's going to do is change. It's just going to literally change all the x's into u's, and you won't have an easier problem at all. So that's one indication. So since we didn't have an actual function up here, a whole expression, we just had an x, that's one indication that you're not going to let the u equal the exponent. The other indication is, we'll look at the parentheses here. We have an inside function here, and what we've done in the past before this lesson is we always let the u be the inside function. So in this case, this is going to be our u, is the inside function. So usually when you're doing exponential functions, the u will be the power, but in some cases it'll just be like the ones we did before where it's the stuff in the parentheses. Okay, so there's my u. Now we're going to find the derivative of u with respect to x. What's the derivative of e to the x? Well, that's just e to the x. And the derivative of 1 is 0, so that goes away. Get dx by itself. And then let's do our u substitution. So I have e to the x. I have u squared. And then du over e to the x. And thankfully, those go away. And now I have a nice simple expression. Now this is a power function, right? So we get to do some old integration that we haven't looked at in a couple lessons. So we just add 1 to the power and divide by that number. Don't forget your plus c. And then we're going to replace the u with what u equals. U was e to the x plus 1. The answer can be written like that, or it can be written as a 1/3 as well. All right, so that's an example. So we've done a couple of examples. This is what I would call the basic one. This is to show you what to do whenever you have a definite integral, which you guys already know. This is to show you, well, this is an example where you have one where the u is not the exponent. So let's see if I have one of those up here for you guys. What should we do here? All right, so now number 2, you guys are ready for that. In this case, I'm going to let you see if you can figure out what the u is. It's one of the 2 options I gave you before. Now number 3 is tricky though. Number 3 is weird, really weird looking. So for this one, I'm going to tell you what the u is. It is this. So let that equal u. Okay. So for I want you guys to do numbers 2 and 3 right now. But what I want you guys to do on number 2 is I want you to figure out what the u is, and then for number 3 I'm telling you what the u is just because it looks a little bit weird. Okay, so go ahead and pause the video here, and when you unpause it you'll see the solutions. So here's those 2 solutions for numbers 2 and 3. Number 2, the only thing that might have been tricky is for you figuring out the u. In this case the u is just the power, right? So remember I told you when you're doing these exponential functions, the u is either going to be the power or it's going to be something in parentheses. In this case, it's the power, so the u would be negative x squared. From there, I feel like it's pretty straightforward, but I guess I'll explain a couple things. Here the x's cancel out, right? And then the 5 over negative 2 comes out to the front. And so from there, it's pretty much basic from what we've done already. Now number 3 is definitely a little bit trickier, so I'll carefully go through each step here. I told you guys that the u was 1 over x. Okay, so if u is 1 over x, we're going to first by starting to transform that into x to the negative 1. That way I can do my power rule when I take the derivative. We take 1 away from the power, so it's negative 2, and then we multiply the front by the negative 1, right? So negative 1x to the negative 2 power, which can be rewritten like this as negative 1 over x squared. So I wrote it fresh here. The derivative of u with respect to x then is negative 1 over x squared. So the next thing I did was I multiplied both sides by x squared to get that out of there. And as a matter of fact, I multiplied both sides by negative x squared to get rid of the negative also. So that left me with that, and then we also multiplied both sides by dx. And so you end up with this expression, which is a little bit different than what we're used to getting at that point, because we had a fraction instead of just a solid number there. So dx, once you get it by itself, should have been negative x squared du. Then we do our u substitution. So we replace this with a u, and we replace this with negative x squared du, and that's what we have here. Then the x squareds go away, and then the negative comes out to the front. Okay? And then after that, you just integrate that, which is simply e to the u, and we have that little negative brought down too. So we have negative e to the u plus c. And then we put the u back, so the u is 1 over x, so it's negative e to the 1 over x power plus c. All right, so there's that. I had one more on mine. Number 4 is a strategy. So even though I'm not giving you one to do on the student practice like this at the moment, I want you guys to just observe the strategy. So when do you do this strategy? So when your numerator has more than one term, you may use this strategy. So when your numerator has more than one term, you might use this strategy. So in this case, I have more than one term in the numerator of this fraction. And whenever that happens, the strategy is to split the numerator up so that you end up with two separate fractions. So here's what I mean by that. Instead of 5 minus e to the x all over e to the 2x, we could split that up into two separate fractions. This is a little integration strategy that can sometimes come in handy. And so I'll make a little note here. So whenever you have something like this, a plus b over c, you can rewrite that as a over c plus b over c. And sometimes that helps when you're doing integration. Okay? And in this case, it will. All right. So let's go ahead and do this a little bit. So I'm going to use an integration strategy. We're just going to integrate both of these separately. Now, usually I don't write it like this. I just do it. But in this case, it's going to help us to write it separately. So I'm going to integrate this, and then I'm going to integrate this separately. And like I said, we've been doing this. Anytime we have multiple terms, we always integrate each piece separately. I just have never taken the time to actually write it as two separate integrals. But I'm doing it now just because it's going to make it a little bit easier to follow what's going on. Okay? Okay, so that's the main strategy I wanted you guys to be aware of. We're still going to finish this problem, but I want you guys to be aware of that strategy. Now, I'm going to leave the right side alone for a minute here. Oops, that is not what I wanted to have happen. All right. So I'm going to leave the right side alone here for a second. Well, maybe what I'll do is maybe I'll write it like this. Okay, now you guys might, well, what the heck did I just do? Remember, anytime you have something in the denominator, you can move it up to the top so long as you make the power a negative, right? That's an old strategy we've learned. So I'm going to tell you right now that's what we do. You might think, gosh, how would I have known that? Well, actually, you may not have really needed to know that at this point. You probably still could have done it without having done that, but I think it'll be easier if we just start that way. So we can actually do something similar over here, right? We can bring that e to the 2x to the top and make that a negative. But here's something else special about this one. Since they both have the same base of e, we can combine these. As you guys know, for instance, right? Like, what if I asked you what's x cubed times x to the 7th? What would you get? You would get x to the 10th. So the rule is that anytime you have x to the a times x to the b, you can say that's x to the a plus b power, right? You just add those exponents together. Well, that's what we have over there. We have e to the x times e to the negative 2x. And so that would be e to the x plus a negative 2x, in other words, minus 2x. So what's x minus 2x? That would be negative 1x. So we can combine these together. Now you guys might be feeling like, oh my gosh, how would I have thought of that? Well, you probably wouldn't have, so that's why I'm showing it to you. But I'm just opening your guys' minds up to some things you can do here. Okay? The main thing I want you guys to walk away from, though, is this little thing here. Okay? So whenever your numerator has more than one term, you can split it up into two separate fractions. Here is where I'm going to stop, and I'm going to ask you guys to actually finish this problem. See if you can integrate it from here. From here on out, there's really nothing different than the problems that we've looked at so far today. So go ahead and pause the video, and when you unpause it, you'll see the rest of the solution there. Okay, so there's I did the integral on the left in green. I did the integral on the right in pink there. And the result was what you see at the very bottom. For the one on the left, I let u equal negative 2x, the power, right? And for the one on the right, I let u equal the negative x, which is the power once again, right? So that's the one on the left and the one on the right. But after we get those, we're supposed to be subtracting them, right? So here's my answer here, here's my answer here, and we're supposed to be subtracting them. Now, technically, after you integrate these, you should have a plus c. But I'm just going to put that on at the very end, okay? So we have negative 5 over 2 e to the negative 2x minus a negative e to the negative x plus c. And once again, when you have double negative, just make it a positive. So we'll do that. All right. I think we'll leave it like that. I mean, you could do more things with this one, but I think that like simplifying it more would just be kind of a pain in the butt, honestly, to mess around with it. So, for instance, some things you could do would be to, move the terms to the bottom, right? And then you could try to get a common denominator. I said I wasn't going to do it, but now I'm being tempted. So we're going to multiply the top and bottom by 2, and I want e to the 2x. Now that means this thing here is being multiplied by another e to the x. Okay, so if I do that, we get a common denominator now. And then we're going to go ahead and combine the numerators. So, I mean, you don't have to do all this necessarily, but hey, can't hurt to review a little bit of basic math. I think the one thing that would have been confusing to you guys about getting a common denominator would have been, how do you get e to the x to become e to the 2x? And the answer is you just multiply it by itself. That would be like e to the x plus x, which is 2x, right? But anyway, there you guys have it. So if you stopped here, that's awesome. If you got there, I'm really happy. I doubt anybody did this, but if you did, that's really cool. Some of you guys probably just stopped here, but if you did stop here, then I would just warn you, make sure that you are understanding those are still being put together with a minus, right? And of course, we don't want to forget our plus c. Something else you guys might be wondering about this, well, shouldn't we have 2 plus c's? Well, I mean, you could. Some people might think, well, if we integrate here, we should have a plus c, and then we integrate here, we should have a plus c, so there should be 2 of them. Well, you're right, but I hope you guys remember what the plus c means. It just means that there was some unknown constant number there before we took a derivative, right? So if I had x squared plus 3 and I took the derivative of that, I would have 2x, and then this goes away, right? So therefore, if I integrate 2x, right, I should end up with the same answer, x squared but we don't know what the number was when we integrate, so we put a plus c. So the thing is that coming back to this thing here, back up a little bit. Some of you guys might be wondering, so why don't we have 2 plus c's? Well, we do actually. When you integrate here, you do have a plus c, and when you integrate here, you get another plus c. But here's the thing. If you take one constant that you don't know, and you add it to another constant that you don't know, guess what you get? Another constant that you don't know. So, I mean, technically, you could have, put the 2 c's over here, but there's no point. The point is that there's just 2 constants, and they come together to make one new constant. And either way, we don't know what it is. So that's why there's no need to write the c twice. I don't know if that was on the minds of anybody out there, but just thought I'd address it. So that's that, and that concludes our lesson. So we will see you guys next time.